Hi, in this video, we want to take a look at stepwise methods for feature selection in logistic regression. Okay, so what we're going to do is that we're going to use an automated approach to select the variables that are going to be in our logistic regression model. And so there's going to be three major ones that we're going to talk about. We'll talk about a few others. First one is forward selection. With forward selection, I'm going to start with a model with just intercept. Then I'm going to look to see what predictor variable I can add that would improve my model. All right, I'll find the best one possible, and then I'll add it. And then so now I've got one predictor variable in the intercept. Now I'm going to look at all of my other predictor variables, see which one would improve the model the most by adding it to the model, and then I'm going to tack it on. And so now I've got two predictor variables in the intercept. Now I'm going to look at all of my predictor variables, and we'll find the best one that would for improving the model by just adding it on one at a time. And eventually, I'll get to the point where either I have all the predictor variables in the model, or it would improve by adding another predictor variable, and then I stop. Okay, so that's forward selection. So we go through, we start with the intercept with no predictor variables, and then we tack on, moving forward to tack on predictor variables until we could not improve the model under this approach. Now, after another way we could approach this is backwards elimination. Backwards elimination, I start with every single predictor variable that I've got, and if it would improve the model, I remove one. All right, and then I check to see if it would improve the model, I'll remove another one. If it would improve the model now, I'll remove a predictor variable. If we remove the current model, I'll remove the predictor variable. I keep on removing predictor variables until I've got the best model I can under the sequence. Now, forward selection is a lot faster than backwards elimination when I have big data, especially if I have a lot of columns. If I have a lot of columns on there, backwards elimination is going to take a very long time. It's not a good choice for big data. Usually forward selection is the way to go. Now, the bidirectional one is the forward back selection, where we do forward selection and every few iterations, we double check to see, hey, maybe I should kick out a predictor variable to improve things. And so this takes longer than forward selection, usually less time than backwards elimination. And it kind of strikes a balance between the two. All right, so forward selection is where we're going to do a stepwise approach. So we're going to go one at a time. Here we're going to be adding a variable to our model one at a time until there's no more predictor variables to consider, or adding on a predictor variable would not improve my model. All right, so here we're going to call this the full model. The full model has all predictor variables in there. And so in forward selection, we're going to start with just the intercept on here. Now I'm going to go through and I'm going to find the predictor variable that would improve my basic intercept model the most. And I tack it on there after the fifth model. And so now at this point, I have a one predictor variable model. Now I'm going to go through all of my remaining predictor variables. I'm going to see which ones, if any, would improve my model. If there's one that will improve it, I tack it on. And so now I have two predictor variables on. And I keep on going through this forward manner of check to see which predictor variable would improve the model the most, and then tack it on, refit the model between each time I put on a predictor variable. And we do this until either the model does not improve or I'm out of predictor variables to tack on. And this is the fastest stepwise approach to compute. And so if I'm in a big data problem. Now the next one is backwards elimination. So here I start with the full model and I check to see, can I improve my model by removing a predictor variable? And if I could, I get rid of that predictor variable. Refit the model, check to see with the current model, would I improve things if I got rid of something? If it would, get rid of that and keep on repeating until either I can improve the model by removing something or I'm down to the intercept. All right, and so this can be slow for large data sets, especially when we have a lot of predictor variables to consider. And so we're removing the variable that has the lowest contribution to the model overall. And so here, imagine I have, this is my starting model. So I've got 7 different predictor variables. And I'm going to go through and remove things. So here, notice that I removed 4 first. So let's say that predictor variable 4 was the least informative in this collection. Then I got rid of it. Now I have this. I refit my model. And then I'm going to, let's say, predictor variable 5 is the least informative, least contributing. Then I get rid of it. And then I keep on doing this, get rid of a predictor variable one at a time until I get to my final model. I'll keep it. Now, don't be surprised when you do stepwise selection if your forward selection and your backwards elimination end up being different models. My experience is usually forward selection ends up being a simpler model with fewer predictor variables, while backwards elimination tends to have more. But I've seen it go every single way possible. And the forward back selection or bidirectional, this is where we do forward selection. And then after so many iterations, I do backwards elimination to see if there's anything I should move. Now, how many iterations forward for each back? It depends on the individual application of the function. All right, so let's go ahead and build some models to show you how you can do this in R. I'm going to show you this approach with base R, the mass package, best GLM, and one more in there. And we're going to use the chronic heart disease target variable from the SA heart dataset from the elementary statistics learn package. Here I'm just doing a little bit of data prep, converting a binary variable to its dummy variable presentation. And I'm going to start by just getting the full model. And so I typically do this when I'm building models, is I use the full model as a benchmark. I use the full model and the intercept model as 2 benchmark models so I can just compare it. All right, so the first way we can do this is with the step function in base R. And so pretty simple implementation. The function is step. I pass the full model first, and then I specify the direction. And so here, it did pretty quick. I got, this is my forward selection model off of this. You can see here are the predictor variables. Now, let's do backwards elimination. This time when I did backwards elimination using the step function, there was a little bit more interesting stuff going on. All right, so for backwards elimination, it went through, it fit the full model, and then it went, hey, what if I removed alcohol? What would the AIC be? What if I removed adipose tissue? What would the AIC be? If I removed systolic blood pressure, what would the AIC be? And it did it for all the target variables, consider removing them each. And then you'll notice that here the none is the full model at this point. My current model takes the none position in this. And so we can see that we would get the best improvement if we removed alcohol. So now you'll notice that alcohol is not in the new formula. So now this is the current model I have. Let's consider removing another predictor variable. All right, well, we're going to go down the line and just consider one at a time each of the models. So when I do this, all of these predictor variables are in here except for the one that has the subtraction sign. Right? See that subtraction? That means that we're taking away the predictor variable on this iteration. And forward selection will have a plus, forward back will have plus or minus depending on what's going on. And so here we consider removing adipose tissue, removing systolic blood pressure. The none corresponds to this model now that has already removed alcohol. And then we can see the rest of them being removed one at a time. All right, so we can see that removing adipose tissue would be the best choice if I'm going to remove a predictor variable. All right, so let's go ahead and remove adipose tissue. All right, and so now I'm going to play the same game. You'll notice that the order of the predictor variables as I go through this backwards elimination or forward selection tends to be the same, but there will be some movement possibly depending on the collinearity of variables being removed. All right, so here it shows that we should remove systolic blood pressure. And that's the only way I could improve my model. So here, this is showing that removing adipose tissue or systolic blood pressure would improve the AIC. Adipose tissue removal would improve the most. I've got rounding off, it says it's the same. That's up to rounding. And so here I'm going to remove systolic blood pressure. You'll notice that it's no longer in the model. And now something interesting happens on this next one. All right, so here I have obesity below the current model that we have, considering removing a variable from, and obesity actually jumps it, which is kind of an interesting thing. And so, under the scheme, we'll go ahead and remove obesity. And at this point, removing a predictor variable would not improve the AIC. Since it wouldn't improve the AIC, I stop. This is my final model for using backwards elimination. So we've got 1, 2, 3, 4, 5 predictor variables in here. Now notice that when I did forward selection, it has more predictor variables in there. We got 2 different models. Forward selection has all the models in backwards elimination plus a few more. And this is because of the order in which the variables were put in. If I would have ended up getting exactly the same predictor variables that was in the chain for backwards elimination, the algorithm would stop. But because it was a different order of insertion into the model, it ended up being completely different. And the forward selection model is bigger than the backwards elimination. All right, now if I do both, what happens here so we're starting with the full model, and we're going to consider removing each of these. And again, I'm going to remove alcohol. And you'll notice on forward back selection, alcohol is tested again. So on this is considering, should I put alcohol back into the model? And so here we see remove adipose tissue, which is consistent with what we had before. And now you'll notice that all the variables that are in there are being considered for removing, but also all of the ones that we've removed are being considered to add back in. The plus sign means, put it back into the model. The minus sign means remove it. And we see removing systolic blood pressure is our best choice. And then, that systolic blood pressure, adipose tissue, alcohol are considered for putting back in, but it wouldn't be an improvement compared to removing obesity. So let's go ahead and remove obesity. And then boom, we get to our final model. And so that's the process. Now, how individual functions, individual packages handle this, it'll be a little bit different. We can do this with AIC, BIC, p-values potentially. Generally, we don't want to be using p-values for statistical significance. That's generally frowned upon, but I would say the benchmark approach is AIC or possibly BIC or some modified version of those too. And so here, let's look at the mass package. Mass package is by far the most common way to do forward selection, backwards elimination in R, by far, hands down. Now, this function gives us more control over what's going on than with step. We can use scope to control what predictors have to be included in the model. And we can say, hey, I want at least this collection and at most this collection in my model. The trace, I control how much output is printed. So if I put a trace that equals 0, I get minimal output printed, which is important when I'm doing things like programmatically or there's errors going on. When I have lots of models that I'm building, typically when I see like errors or warnings, usually warnings come up. Well, if I get a warning, I'm just not going to use that model. And so I really like overwhelmingly don't worry about that. I put trace equals 0. Now K is the penalty parameter. K equals 2 is IKE's information criterion, and K equals the log of our observations is Bayesian's information criterion. Bayesian's information criterion has a larger penalty for any meaningful data set. And so BIC will prefer to have fewer predictor variables. Our models will be more parsimonious when we do BIC. And then let's go ahead and do this. And so I'm going to run step AIC forward selection. And you'll notice, boom, I got the same as I got before. And this is going to be very, very similar to what we had previously because I left the parameters on AIC. I didn't do BIC. I want to leave things very similar so that at the end we can see the similarities between them to keep things consistent. But if I put a k equals log of n, I would be BIC. If I put k equals 10, the model would want to have fewer predictor variables than AIC. The bigger the k, the fewer predictor variables I'll anticipate having. And this will run through the process of getting through and removing one at a time until we get to the point that there is no improvement to be had by removing predictor variables. Now for both, same game. Just go through and subtract or tack on predictor variables as appropriate. And I get my final model. All right. And so that is how we would do it with the base R package or base R or with the mass package. Both are very common to be used. Another way that we can approach this is use the best GLM package. And it has a namesake function that works very well for us. Now, I could not see a straightforward way to make predictions with this package. So I would shy away from using this as the actual model. I might use the exhaustive feature if I want to find the best model, but I wouldn't use the actual fitted model. I would take the exhaustive fitted version and use that with GLM to fit my final model. So because I'm just more familiar with it, more comfortable with it, I can work it out. Now, something that's nice with this function is that I can specify, I have a range of options when it comes to specifying the criterion for kicking things out. And this does cross-validation for us. It does exhaustive search. This package actually has a good number of features to it, but it wasn't as straightforward for prediction as I had hoped. And so, we have forward selection, backwards elimination. We have sequential repetitions. And we have exhaustive. Now, exhaustive is going to go through all possible models. This can be a very, very large set. Remember that if I have n predictor variables, then I have 2 to the n possible models, and that includes the full model. That includes the intercept only model, and it can take a long time to compute. The 2 to the power of the number of exponents, it can take a while. This can grow by quite a bit if I get more predictor variables in there. Generally, like overwhelmingly, statisticians frown upon using this, but I know that a lot of people want to use it. My experience is that the exhaustive search is really not going to give you that much better of a model than forward selection or backwards elimination. Honestly, forward selection, backwards elimination, forward back end up producing pretty similar actual predicted values, and it's not. I don't think it's really worth fussing over unless you need to squeeze out every bit of predicted value from your model. I could not find a straightforward way to run predictions on this. There are functions in this package that say predict in them, but they didn't really work out. It seemed like it was not for the best GLM class, so I'm just not worrying about that later in this video. Now, StepReg, what this package does is it provides a few different ways to do stepwise selection. The thing that's nice about this package is that we have a wider range of tools for selecting should a variable be in the model or not. And so that's very nice, very clean for us if we want to use it. Once again, I didn't see a straightforward way to make predictions with this. And so if I wanted to use this for going through and fitting a model, I would use this for figuring out the coefficient or the predicted variables to keep and then fitting with GLM. more than likely. And so we have forward selection, backwards elimination, forward back, and we also have a score method also. And so, this gives us, some variety on how we can approach this. All right, so now let's go ahead and compare the models. Unfortunately, with StepReg and BestGLM, I couldn't find a straightforward way to do a prediction with the package, so I'm going to skip over this. I'm going to just go over the GLM full model. I'm going to look at the base R stepwise selection, and I'm going to look at the mass package version of the models, and just to show what these look like. And so what I'm going to do, I'm going to take all of my models. I'm going to so remember, it's a good idea when you have a lot of work going on to keep similar objects into a list. That way I can iterate over the entire list very quickly to get tasks done. I'm going to do that here. And so here I have all of my models in the list I call list model. And I'm going to go through and I'm going to run predictions on each of them. I'm going to get the model probability of success from each of these models. Now, after I get those model probabilities, I'm going to go through and I'm going to convert values greater than 0.5 to saying heart disease, lower than 0.5 to not heart disease. And then I'm going to create the confusion matrix for each of these, just so that we can compare it. And so here for the full model, I have a 7.34. For base R for selection, 7.34. All right, not much of a change. Backwards elimination, 7.742. Stepwise, base R, 0.742. This is forward back. And then mass package, 0.734. Then backwards elimination with the mass package, 0.742. Hey, we've seen that number before. Forward selection, forward a back selection, 0.742. And so we can compare these different models. And also I can consider sensitivity, specificity, balance accuracy, things like that as I work through this. Also, I can go through and I'm just going to plot the ROC curves for each of these. These are in the order of the list that I have on there, and we can just see, we can evaluate how would the model perform if we were to change the cutoff. I use the cutoff of 0.5 to say heart disease, but maybe that's not appropriate for our project. The ROC curve helps us decide on what would be the best cutoff overall. The ROC curve evaluates different possible cutoffs for declaring the classification. Okay. Ideally, we would see a perfect square. We would want the curve to be as high and to the left, as high up as possible, as far left as possible. All right, so for your homework, go through, fit forward selection, backwards elimination, or back models. Submit it on web courses. That's all I've got for you. Life is short. Do math.